Hi and welcome to part 2 of the rate law videos. This is the algebraic approach to rate law, whereas part 1 has the ratio method or common sense method. So we're going to attack this problem and we're looking to sort of fill in the order of reactants. So we're going to use an M to represent the order of A, and we're going to use a N to represent the order of B. So first of all, I'd like to just start off with trial 1 and 2 because I see for B that they're actually consistent. This is fantastic. So I'll start there with trial 1 and 2. So here we're gonna need a placeholder for rate, placeholder for K, placeholder for A, and for M. And I'm putting these little dots here just to signify like multiply signs, but instead of using an X, because then that starts getting tricky. So I'm going to put all the values for trial 1 on top and all the values for trial 2 on the bottom. And I'm picking trial 1 for on top because the rate is bigger in trial 1 compared to trial 2. So I like to use I like nice big whole numbers. And so if I divide this little number up into the big number, then I'm going to get some kind of bigger juicy number rather than like a decimal number, which I have no interest in. The value for K is actually going to be the same. We don't know what it is, but we don't need to because it's at the same temperature. And it will cancel itself out, whatever it is. For A, we are going to be putting in 0.25 up above, 0.10 down below, and this is all going to be to the power of M, unknown at this point in time. B, 0.10, and this is all to the power of N. Now, when you get a situation like this, where you have 0.10 over 0.10, that is basically canceling itself out. It's becoming 1. So what we want to do now is actually do our divisions in these two spots and see what we're really talking about here. So top divided by bottom gets us 2.5 on this side. And also top divided by bottom gets us 2.5 on this side. But we know it's to the power of M. So we want to ask ourselves, 2.5 to what power makes 2.5? And we know it's not 0. And we know it's not 2. So therefore, M must be equal to 1. Therefore, A is a first order reactant. So let's take a look at B and see what we can make of that. And this is where your hand is forced into using algebraic method because A never stays still. A's never got 2 trials where it's consistent. A is always variable. And so we can never really use the ratio method or the common sense approach to solve for B in this example. So this is sort of why I picked it for us. And for me, I'm going to pick 3 and 2 because I like 3 seems like a nice big juicy number, and like maybe 2 is going to be able to divide into it nicely. So so I'm going to, for myself, I'm going to put 3 on top. So I will be putting the rate for 3 on top, the rate for 2 on the bottom. Again, why did I pick that? Because I like this looks really like a big number, and then I'm putting a nice small number up and into it. Again, we're going to see this value for K, which we can cancel out. A, we know A is a first order reactant. So let's take those values for A. And we're going to take 0.20 up on top, 0.1 on the bottom, and it's all to the power of 1. For B, we want trial 2's values here, and trial 1, or trial 2 on the bottom. Trial 3, sorry, this is trial 3, and trial 2 on the bottom. So the thing that we're trying to solve for here now is the order of B. What is the order of this reactant? So let's do some division. If I do top divided by bottom, brilliant, it becomes 6. Here we have a 2. And here, if we do our division, we'll have 3, and it's to the power of n. So I want to kind of get n by itself, so let's divide this by 2, divide this by 2. So 3 is equal to 3 to the power of n. So what is n? N must be 1. So B is a first order reactant. So in terms of our rate law, how would we express the rate law? We would say rate is equal to K, and then we would just put our AB here. And that's representing the 1 and the 1 there. So we've got our final answer.